Let's have a look at this problem. Consider the following roller coaster. If the car's velocity is almost at zero at point A, what is its speed at point B? And it says here, ignore friction and air resistance. For us to solve this problem, we are going to consider no losses. No losses due to friction, air resistance, or heat. In other words, all energy is conserved. What this means is all the energy that is being put in here is equal to all of the energy that is put here at the end. All the energy at the beginning equals all of the energy at the end. All energy is conserved. We're going to ignore any losses. Having said that, let's have a look at what is given. We're given an initial velocity given. Given that its initial velocity, the car's velocity is almost at zero. Almost at zero up here. It's going to have to move a little bit in order for it to go down. So somebody just stands up and tips it a little bit, and then off it goes. So in effect, the velocity here is at zero. So initial velocity is equal to zero. The height from here to there, this is the initial height where the roller coaster is starting. Height initial is equal to 25 meters. The final velocity is what we want to find here at point B. And what is its speed at point B? That we don't know. And the height at point B is given to us here as 12 meters. And this here is the reference in order to determine height. Reference point. I'm going to take the reference point here as the ground. From the ground up to where the cart originally begins is 25 meters, and we want to take our measurement at the end for final velocity is going to be 12 meters. And then we have mass. Well, let's have a look at the equation we're going to use. Here's our equation. And this is the conservation of mechanical energy equation. What this means right here is all energy is conserved. There are no losses. So we're not going to have to put in extra terms for loss of heat or loss of friction due to friction. Here's our equation. I'm going to write this down. mgh final plus 1/2 mv final squared is equal to mgh initial plus 1/2 initial squared. What we have here is a combination of kinetic energy and potential energy. So the total energy here at the end is equal to the total energy at the beginning. Everything is conserved. No losses due to heat and everything else, etc. Little subscript f represents final. Little subscript I represents initial, the starting point. Sometimes you may see this reversed, where the initial is on this side and the final is on that side. It really doesn't matter, just a preference. And sometimes you'll see this equation written like this. Is equal to mgh with a subscript with a 0. It's pronounced not, mgh not plus 1/2 mv naught squared. This is an old English term. Sometimes it's written NAUGHT. It's an old English term meaning zero, and it represents the initial velocities, the initial height. I prefer to use the little letter I. More modern textbooks simply took away this. This is traditional, and replaced it with the little letter I for initial. And I'm going with this convention right now, the more modern one. But you may see subscript 0, and that just simply means the initial point, the beginning. And it's pronounced not, mgh naught, height naught, or v naught squared. So let's have another look at this. We have mass. We talked about mass. Now every one of these terms has the term of mass in it. Here's mass, there's mass, this is mass, and that's mass. So every term has mass in it. And mass is in the coaster right here, plus everybody inside of it. And if we make the assumption that the coaster plus everybody inside of it goes all the way down here, up and around, and all the way to this point, and nobody falls out, everybody is still in the buggy as it reaches here. Therefore, the mass is going to remain constant. The mass will be the same all the way throughout. And if the mass is the same throughout, we could, either one of these equations will do, I'll use this bottom one here, we could divide mass from every term. As long as every term has the term mass in it, we can do this. If there was a separate term here that didn't have the mass within it, oh, that would be a little bit more complex. But for this case right here, because every term has mass, so whatever you do to the left-hand side, you have to do to the right-hand side of an equation. And so they all cancel out. So this will reduce, I'm going to use this terminology up here, this will reduce to GH final plus 1/2 velocity final squared is equal to, and I'm using this one, GH initial plus 1/2 velocity initial squared. So in this scenario, when the mass remains constant throughout the system, we can eliminate mass. And that simplifies the equation some. And what's left over, well, this is what we have here. And of course, we have to look for base units. Everything here has to work in base units. And the only units we really have here is the meters, the height. In meters, so everything is good. Nothing left to do now but take these numbers, not mass, and plug them in here. And we know what G is. G is a constant, 9.8 meters per second squared. In the case of energies, and this is energy, conservation of energy, conservation of energy. For conservation of energy, the value of G is always positive. Always positive. So putting in the numbers, and I'm going to avoid, I'm not going to put in the units, they will properly cancel out, just to give me some space. G is 9.8 times the final height, H final is 12 meters, plus you get 1/2 the final velocity squared, that is what I want to find, so it remains, is equal to 9.8 times the initial height. No, I made an error there. The final height is 0. No, the final height is 12. That's correct. Plus the initial height of 25. Plus 1/2 times the initial velocity, and that one is 0. Doing some rearranging on this, I want to isolate V final. This is added to the left. I'm going to subtract this then to the right. If I need to subtract it from here, I need to subtract it on the right-hand side. This term drops out altogether. So reducing this, I'll get 1/2 VF squared is equal to 9.8 times the 25 minus this term. This 1/2, that is in the denominator. So if I were to take it out from there, it looks like this, divided by 2. In order to isolate final velocity, I need to multiply both sides times 2. And it would look like this. If I multiply this times 2, the left-hand side, I need to do the right-hand side by 2 as well. So VF squared is equal to 2 times everything. Look like that. And this is squared. So I take the square root of the left-hand side, take the square root of that. That will change this to VF. And then whatever I do to the left-hand side, I have to do to the right-hand side. Take the whole thing has to go under the square roots. So it looks like this when we're finished with it. Square root of VF squared is simply VF, final velocity. And then I have to find the square root of all of that. Minus 9.8 times the 12. Putting this in the calculator, press equals often, follow the rules of BEDMAS, and the number will be 15.96246. And the units of velocity, even though I didn't work out the units here, we know unit of velocity will be meters per second. And lastly, looking for sig figs. And we go back to the original question, and not much is given there. Here, we're given 3 significant figures for that one, and we used 3 here. So we'll go with 3 significant figures for the final answer, 1, 2, 3. Look at that last one. So this bumps it up to a 0, which bumps this up to a 6. 16.0 meters per second.